Hi students. So today we start Math Question Bank 24. Today I'm going to look at four questions and we are going to solve these problems related to the predator-prey differential equation. Now this is a particular system of two equations which is very important, and very often you are asked questions on these equations, and if you are a person who wants to test students on simple differential equation, specifically on equations which cannot be easily solved, then this set of equations is for you. I'm Dr. Ganguly. So let's first take a look at these equations, and I have these two equations here in red. You can see that these are simultaneous differential equations. The variables we need to solve for are x and y. We need to find x as a function of t, y as a function of t, and you see that a, k, r and b are constants. Now of course there are some students who may know these equations, so you can frame the question as to write the predator prey equations and then look into it in more detail, or you can simply write the equations on the board and you can ask the student to look further into these equations. Now these equations are also known as the Lotka-Volterra equations. So that's one more name for the predator-prey equations, because actually there are many different predator-prey models. So I think it may be better in some cases to refer to this as the Lotka-Volterra equations, but this is the simplest form of the predator-prey model, which is very important in population dynamics and ecosystems. So now let us take a closer look at these two equations. So here x represents the population of the prey, y represents population of the predator, and r, a, k and b are positive constants. Now let us look at each of these equations and let us only look at the red part of these equations. So if we were to look at a population which consists only of prey, for example deer, then we can have this red part of the equation which can model it, that is dx by dt is kx. Now the solution of this is going to be the exponential function. So what's going to happen, that because there are no predators present, the population of deer is simply going to go up exponentially. I'm going to show this in the next couple of slides graphically also. Now let us imagine a situation where there are only predators, all the prey have disappeared. In this case, the population of predators is going to simply decay. So the equation is going to be dy by dt is minus ry, the equation in red here. So this is the case where there are no prey. So unfortunately the tigers here do not have things to eat. So after some time they are simply going to die out. Now what happens in the predator-prey equation is that we add these two terms. They depend on a and b, and a and b are of course the coupling terms. So in the first equation, the negative axy term means that the prey population is decreasing because the predators are going to eat the prey every now and then. So that's going to keep a check on the prey population. Similarly, if we look at the plus bxy term here, here the predators are going to keep on increasing because as they eat prey, they have more food in their system and therefore they will reproduce and their population will grow up. So these two terms actually ensure that the predator and prey population remain in some kind of equilibrium, and therefore what happens is that the growth of the prey is bounded and the growth of the predators, or the negative growth of the predators, is also kept under check. Now you can see that these are two coupled simultaneous equations. These equations cannot be solved explicitly in general cases, and therefore we can often solve them using numerical methods. But in today's lecture, I'm going to only look at how you can get a lot of insight into this equation from some simple techniques which are often used to analyze differential equations. Now, just to review some of the equations we studied in our previous question bank, you remember we solved the equation of the form dy by dt is y. And so in that case, what happens? You get exponential growth. So let us say we have a normalized deer population that is at 1, y0 is 1. And then what's going to happen is that there is going to be an exponential growth in the prey population. So this is what would happen if there was a prey population but there was no predators. So predators do play an important role in that they keep the population in check. Now the second equation we had solved in our previous question bank was dy by dt is minus y. So that equation had a form given by this. So this is a decay equation. So in this case, let us say there was a normalized population of 1 here, that is y0 is 1. Then there would be an exponential decay in this predator population. So essentially these tigers would have nothing to eat, so their population would decline. So this is given by y is y0 e to the power minus t. So now let's turn to more mathematical question here, and that is find the critical point of the predator-prey equation, or the critical points of this equation. Now critical points are also sometimes known as constant solutions, sometimes they are known as equilibrium solutions, sometimes people say these are stagnation points and so on. So essentially we have these two differential equations and we have to find the critical points. Now the critical points of a differential equation happen when the derivatives become zero. So essentially in that case, the problem here is very simple. We simply have to take the equation for dx by dt and set it equal to 0, and the equation for dy by dt and set that equal to 0. Now once I set these two equations to 0, these equations in red, I can rewrite these in this form here. Now if we take both these equations, say I take kx minus axy, I can take x out, and therefore I have k minus ay inside the bracket, and this is equal to 0. In the second case, what I can do with the minus ry plus bxy term, I can take y out and I get bx minus r. This entire thing is equal to 0. Now, essentially, I know from these two equations that I could get two solutions. One, of course, is x is 0, y is 0. That would solve this system and that would be a critical point. The second solution, which is more interesting, is that x is going to be r by b and y is going to be k by a. Now the first solution here is kind of a trivial solution because it simply means that the population of prey, which is x, and the population of predators, which is y, are both simply 0. So this is not a very interesting solution. It simply means there are no prey, there are no predators. Now the second solution is more interesting. In this case, we have the numbers r, b, k, and a here, which are the coefficients of this differential equation. So this particular equilibrium point would be something at which the population can exist in a very nice manner. So let's put some numbers on this equation to get some typical values. So here the question is find the equilibrium solutions of the predator-prey equations given by these two equations here, and now we have got some numerical values here. So 0.08 minus 0.001 minus 0.02 and 0.402 here. So let's try to find the equilibrium solution for this system. Now, of course, you know from our previous problem that you have to simply set the derivatives dx by dt and dy by dt to 0 to find the equilibrium solutions. And the moment we set this, just like our previous slide, we do this particular solution here and we get x is 0, y is 0, the trivial solution. And then we also get x is 0.02 by 0.402, that is 1000, and y is 0.08 by 0.001, that is 80. So the first solution simply says that there are no tiger and no deer in this forest, and so it is in a complete state of equilibrium. The second case is that there are 1000 prey or deer in the forest and there are 80 tigers, which are the predators, and so this is also an equilibrium solution. Now in most cases this is something which seems reasonable because you are going to have a far fewer number of predators than you are going to have prey. So in this case you have only 80 tigers and these are sufficient to keep a population of 1000 deer in check. So in this kind of numerical situation, the prey and the predator are getting along fine, at least as far as equilibrium and math is concerned. the prey may not be too pleased with their situation, but that's the reality of the world we live in. So let's come to question number 4, and this is to write the predator prey equation in terms of variable x and y only and then solve the resulting equation. Now, like I mentioned before, you cannot exactly solve this equation because there is this coupling present here because of the xy terms. So what we are going to do is we are going to get rid of time in these equations. Now, that's something which is not very difficult to do. Let's do it in the next slide. So what I do is I take these equations and I apply the chain rule here. So I will get dy by dx is dy by dt divided by dx by dt. So immediately from these two differential equations, I get the new differential equation here. Dy by dx is this expression here. And all I have done is applied dy by dt and dx by dt in this formula in blue. Now you can see here that this equation is pretty nice and maybe we can solve it, but of course we have got rid of time. So in some cases we may actually like to see the response of the system, that is x as a function of t, y as a function of t, but here we would be quite happy if we could get y as a function of x. So let's see if we can do that. So we take the differential equation and looking at it carefully, we realize that this is a separable equation. That means I can get all the terms involving y on the left hand side and I can get all the terms involving x on the right hand side. And after I do this, I can essentially spread this out. I can expand the terms on the left hand and right hand side, and then I can integrate both sides of this equation. Now, of course, you know that terms like dy by y immediately give me log y, and terms like dy will give me y. Here dx by x would give me log x, and dx would give me x. Now, do remember that whenever you are doing some integral on log, it's always going to be log of the absolute value of y because log is only defined for positive numbers. So now we get this equation here in blue, and I can write it in this manner. I can take the terms involving x to the left hand side, and so I get this equation in blue here. So we have these terms here involving x, involving y, and then we of course have the constant which has come out because we have performed the indefinite integral. Now let's come to the fifth question, which is plot the phase planes for the predator-prey equation. Now these were the two equations here, and I'm going to explain to you what exactly are the phase planes for this problem. So what happened is that we got the equation in terms for dy by dx, and then we found the solution out in this form. Now in this form, the solution can also be expressed as f function of xy is c. Now, if we look at this function of x and y, we can write it as follows. Now, it would be nice if we could plot this because you can of course realize that this is going to be a nice function, hopefully, in the xy system. So if we were to plot it in the xy system, we would be able to get some insight into this equation. Now, these are known as the phase plane plots. So I tried to do this in Excel and so on, but I think you'll need to write some code here in Python or MATLAB to do this. So essentially what I did is I went to Wolfram-alpha on the web and then plotted this equation. Now, if you are doing this particular question and you are doing it in Team or you are doing it in Zoom, then you can ask the candidate or student to actually go to any place on the web and try to solve it. And in these cases, Wolfram Alpha, which is also behind Mathematica, they let you do this problem. So essentially, I entered the equation here. This is the equation fxy, and I plot it. So I get a plot like this in terms of x and y. Now, this plot is interesting. You can see some contour here, but it would be nice if I can see it in only the 2D plane, that is the xy plane. And that's what I'm going to do in the next slide. So this is what I have plotted here, or basically it's the same output, but this time I have shown you the more interesting contour plots. And you can see here there is the y-axis, there is the x-axis. The x-axis is of course the prey, the y-axis is the predator, And you see these nice looking plots here. These are the contour plots for the system. Now these are all coming out as closed plots for the predator-prey equation. And we are going to take a zoomed view on this square so that we get a good idea about the phase plane. So this is the zoomed view on the same equation. Now you can see here that on the left hand side we have y, on the right hand side, or rather on the x side we have x, and so this is the prey. This goes up to large numbers, and this is the predator. These are somewhat restricted in number. We see that this graph is known as the phase plane, and we see that there are many closed curves here. So this is a cyclic population. That means the predator prey population is cyclic. So if we go on any of these curves, we see that there are points where the prey goes up, the predators go up, and they come down, and so on. But it's a cyclic system. Now we can see that as far as the equilibrium point we obtained, that was x is 1000 and y is 80, that's the deer and tiger population. They are contained within this curve. So this would be 1000 here and some point like this. So it's contained within all these particular curves out there. So that's the equilibrium population. Now this kind of phase plane, sometimes also known as a phase portrait, this is very important. There are many equations out there which you cannot actually solve mathematically, at least without resorting to numerical methods like Rangekutta and so on. You can of course do that in MATLAB. If you check in Google for solutions of predator-prey equation in MATLAB, you will actually see code out there which is going to give you solution in the form of xt, yt. You can do that as a homework problem. But if you can't do that also, you can get these nice plots. And through these nice plots, you can get a lot of insight into the differential equation, though you may not be able to solve it explicitly for xt and yt. So this was today's video about the predator-prey differential equation. Like I mentioned before, many differential equations are out there. Most are hard to solve using any classical method. So most of the time people resort to numerical methods to solve these equations. But there are many equations from which you can get a lot of insight into the behavior by looking at the phase plane and so on. And so these methods are always useful. Sometimes you can find the critical point of the equations. You can also look at stability and so on. So at least today's video we got started at some of these points. And of course, if you are somebody who is trying to ask questions to different candidates out there to figure out their knowledge about applied mathematics, then this is a good question to ask. In the next video, I'm going to talk about the wave equation, which is probably the simplest and one of the most important partial differential equations. And that is going to introduce you to the very basic thing about partial differential equations. And even if you know only calculus, these videos should be amenable to you. So you should be able to figure out most of the things in the video by just having high school knowledge of calculus.